Hi, my name is Binish Patel, and I work as a research analyst at the Maryland Psychiatric Research Center under the supervision of Dr. Peter Kochanov. In this video, I'll be demonstrating how to create a phenotype file as well as how to perform univariate and multivariate analysis. It's super easy, so let's get started. Creating a phenotype file for the SOLAR analysis directory is relatively simple. Here is a sample phenotype file that I have created. In terms of the header, it must include an ID which matches the IDs found in the pedigree file. This file will typically include the age and sex, which are usually covariates, and then here I have various phenotypic variables, so average FA values and LPA. Now this file also has class, but that's not really necessary. What's important here is having the IDs, and then typically your covariates, and then your phenotypic variables. Now when saving this phenotype file, the only data that SOLAR supports is the CSV format, otherwise known as the comma-separated value format. And if you're using a Mac, make sure it's in Windows. I've already saved this in the CSV format, but make sure that you save yours as well. Now that you have your phenotype file, how do you go about performing your analysis? First, you have to start SOLAR. So here I have SOLAR brought up, and I'm going to maximize it so hopefully you can see it better. I would suggest you create a separate directory whenever you're performing these analyses because there will be a lot of output files, but because I want you to be able to see the output files easily, I'm just going to CD to the desktop so that you can see the output files easily. Then you must load your pedigree file by typing load pedi and then typing the name of the file. So in my case it's lpa pedi.csv. And as you can see, files are generated once you load your pedigree file. And just in case you need to know, I did create a video for the pedigree file, so if you want to check that out, please check that out so you know exactly what you need in that file. Now, in terms of the files that are generated, two that may be of use to you in particular are the phi2gz, and this file essentially contains the kinship matrix. And then the house.gz file contains the shared environmental matrix. After that, you can just load in your phenotype file by typing load pheno and then the name of your file. So mine is lpa_pheno.csv. Or your phenotype file, all the header values will be shown, so you know that it's properly loaded. Now you can go about performing your univariate analysis. So start by assigning a trait which you're interested in for calculating heritability. I'm interested in average FA, which is in my phenotype file. So all I do is type trait average FA. Then I can assign covariates by typing covar age sex age times sex. Then run the polygenic command by just typing polygen, which will conveniently show you a summary of results. It's very quick, it's very fast. However, as you can see, I got a warning sign. So even though I did get a heritability value, my warning sign tells me that my standard deviation is below 0.5. Although my residual kurtosis is also within range, sometimes that may also give you warning values. An easy way to solve this basic statistical problem is by enforcing normality of distribution in order to have a valid heritability measurement. You can inverse Gaussian normalize this data by doing the inorm function in Solar by typing define and the name of your trait that you want to assign. So mine is average FA inorm, since that's what I'm going to label it as, space equal sign space inorm underscore average FA. So this, when you write average FA inorm, that's what you're naming the trait, and then inorming the trait itself. So you can honestly label this whatever you want. Once you have that done, you have to type your trait again. So it's average FA inorm. And then identify the covariates by typing in covar age 1, 2, 6. And then just typing the polygen command. Oops, meant to do poly. Be careful, make sure you type it in correctly. And voila, we have all of the correct values. So now there are no warning signs, and you have the heritability values. Now, in addition to this output and heritability value and p-value that you get, a directory is named after the trait. So average FAI norm. There was one named before you normalized it, but this is more helpful. So with average FAI norm, it contains many files, some of which may actually be of use to you. It contains both .mod and .out files. The .mod files contain model parameters. For instance, the null0.mod contains the null0 model, including the results for each iteration for MLE processing. The polygenic residuals file contains the residual values after correcting for covariates. The file polygenic out right here contains the copy of the results. The no covariate out contains the output of the data with no covariates, and then the spore mod and polymod are just model files. So these may be of use to you if you need. Now that we've discussed univariate analysis, let's talk about how to perform multivariate analysis, which is where Solar really shines. Multivariate analysis is useful if you want to see if genetic variance or heritability is shared between two traits, which often suggests that there's a common genetic or environmental cause. All you need to do is use one more trait. So since I've already looked at average FA, I'm going to now look at results for LPA1, which is another phenotypic value that I'm interested in. So you just repeat what you did before one more time. So I'm going to do trait LPA1, identify the covariates by writing covar age, sex, age times sex, and then polygen. But once again, we have a warning sign because residual kurtosis is too high, so we will just normalize this by writing define LPA1 inorm equals inorm LPA1. Identify the covariates by typing age, to number sex, and then trait LPA1 inorm, and polygen. And now everything is fine. All you need to do for the multivariate analysis is type model new, type trait, average, FA inorm, LPA 1 inorm, covar, age, 1, 2, number, sex. And just in case you're wondering what this covaries, it's essentially covaries age, age squared, and then sex and age by sex. Then, after that, you type polygen, test, row E, test, row G, and test, row P. By the way, just in case you're wondering what these commands stand for, the test row E calculates significance of genetic correlation. The test row G calculates significance of environmental correlation, and test row P calculates significance of the phenotypic correlation, which is essentially the Pearson's correlation coefficient. And now when you enter, you will get a very lengthy analysis. Row E, which provides you with the Pearson's environmental correlation coefficient. Row G will give you the Pearson's genetic correlation coefficient. And then row P, right here, as you can see, will give you the Pearson's correlation coefficient. This in particular is a bivariate analysis since we were just looking at 2 traits. But you can obviously have more traits as long as you have enough statistical power to carry on with it. And that is all. I hope you found the tutorial helpful. If you have any questions, comments, or concerns, please don't hesitate to leave a comment below and we'll get back to you as soon as possible.